right, let's go and get started here. Your homework was to complete page 265, questions 12, 13, 15, and 17. I'm going to have that homework out. Yeah, combine check. Excellent. Good. All right. Continuing our discussion of sound. Again, worked a lot with the Doppler effect yesterday. Moving forward here, question number 12 says, how does the idea of power apply to sound waves, and how is it defined mathematically? Audrey?
Intensity is the idea of power that applies to sound waves. It is defined mathematically as I equals P over A.
Good. So we think of it the intensity of waves as opposed to power. It's actually power per unit area. Good. Number 13, how does intensity vary with the distance between source and receiver, Michael?
The farther the intensity has to travel, the less powerful it becomes.
Okay, yeah, indirect variation. There we go. As the distance increases, the intensity decreases. All right. Did you have anything different, perhaps, Kendall?
Mm-hmm.
No? Okay, just curious. Audrey, do you have anything slightly different?
Mm-hmm.
Okay. Number 15, what term describes our perception of intensity? Kendall?
The term to describe our perception of intensity is loudness.
Very good. And number 17, what are the advantages of measuring intensity in decibel units? Audrey?
An advantage that is good in measuring intensity in decibel units is that it's just the noticeable difference in sound energy and can basically rate any sound.
Very good. Excellent. All right, we'll get into some of that today, some of it in our next lesson. Let's go review some things we've talked about recently. Been talking about sound. Said that sound is a wave. Specifically, class, it is a three-dimensional wave, and it is a longitudinal wave. It is a series of compressions and rarefactions. We said that sound travels differently through different media. 3 factors affect the speed of sound. Audrey, can you give me all 3?
Density, hardness, temperature.
Density, temperature, and hardness. 2 of those are positive factors. Kendall?
Hardness and temperature.
Hardness and temperature. You increase the hardness or rigidity, you increase the temperature, you're going to increase the speed of sound. Obviously, then density is the negative factor, where if you increase density, you will decrease the speed of sound through the medium. We said that as a wave, sound wave travels, it's just a series of compressions and rarefactions, but if the object emitting the sound wave is moving forward, it will push those compressions and rarefactions closer together. It'll compress the wavelength, thus, Michael,
The frequency is higher.
increasing the frequency, making the frequency higher. To the rear of a moving object emitting a sound, then that wavelength lengthens, which makes the frequency class lower, decrease, right? We also said it couldn't be not just the source that's moving, but the person hearing or the thing hearing the sound could also be moving. We said if the source or the observer is moving toward the source class, that will cause a perceived higher frequency because you're hitting those wavefronts more rapidly than you would if you just stood still and let them hit you. You're going and hitting them as well. And so that increases the frequency. Or if a person is going away from the source of sound, that will cause a lower frequency. What's that equation? We did a lot with it yesterday. What is that Doppler effect equation? Kendall?
F sub L equals F sub S times V sub R plus V sub O over V sub N times V sub S.
There we go. So, and I said the V sub air is something we'll calculate. Unless it's 0, then we know class it's 331.5 meters per second. If it happens to be 25, that was another one that we memorized. 346, 0.346 if you want to be really, really exact. Though as Audrey found out, even if you don't have a particularly exact number here, the math still works out pretty closely. We said that the VO and the VS, those are velocities. Those can be positive or negative. What's the rule, Michael?
If they're approaching, it's positive. If they're leaving, it's negative.
Good. If either one of them is approaching, that particular velocity is positive. If that particular object is going away, then that particular object has a negative velocity. What if, and we only did this once, usually I gave you the source's frequency and we had to tell what frequency the person would hear. What if I knew what frequency was heard and I wanted to know what the actual frequency was? What would we have to do? Audrey?
You alternate the V sub air. Well, you flip it.
What's the word? It's not alternate, but if you flip it, you multiply by the reciprocal. There we go. We multiply by the reciprocal of this. We have the v sub air minus v sub s over the v sub air plus v sub o, if we wanted to go the other direction. And then yesterday we also looked at if an object is traveling, as it travels faster and faster, again, that compresses the frequency higher and higher and higher, to where if the object actually traveled at the speed of sound, for instance, maybe the object was traveling at 331.5 meters per second in 0 degrees Celsius air, the wave fronts would literally be right on top of each other. All the compressions would coincide, which would produce something called a, well, we would hear a sonic boom, but the sound wave would be called a shock wave at that point. At or above the speed of sound, shock waves are produced, which the next question is going to be, what do we hear? Sonic boom. And again, that super, I almost used the term, speeds at or above the speed of sound cause are called supersonic speed. It's shock speed. Supersonic speed and or Mach speeds. And I got a few videos for you to watch, so if you would, go ahead and pause this video for a moment. There are 3 video links in the description of the video. I want you to watch those, and then you can resume the lesson. All right, well, thinking about the videos that we just watched, one of the things I wanted you to notice, if you look at the front cover of your textbook, you'll notice a picture of a fighter jet. And I believe that's an F-18 fighter. Obviously, we watched a video about an F-16 fighter. You notice that weird cloud. Have you wondered about that this year, perhaps? That's a cloud that's formed by compressed air, formed by a shock wave. Did you notice on some of the F-16 videos, this weird conical cloud when they were showing it hitting that supersonic speed? And you can go on YouTube and look at other different videos as well of the F-18. The Blue Angel pilots will occasionally hit supersonic speed, and you'll see this shock wave form. I watched a video, I don't have it for you, but I watched a video where an F-18 hit supersonic speed over the water. It's kind of cool. You watch this, just all of a sudden you hear this boom, you see this cloud form, and the water, like really, really big splash in the water right at that moment. So, and kind of cool stuff you can look at there. But hopefully those videos were interesting to you. And again, just kind of interesting too, thinking about what could come about with supersonic transport, actually flying supersonically just as a passenger, right? Not having to be an Air Force pilot, saving lives or anything like that. So interesting stuff there. We also get the idea that sound has energy to it, correct? Waves carry energy. It's a transfer of energy, right? I speak, right? There's a series of compressions and rarefactions as my lungs force air. That energy travels through the air, and it makes your eardrums shake, right? Just a little bit of vibration. Now, if I yell louder, right, I can make them perhaps even hurt. If I got right up in your ear and yell, that would hurt even more. But we know that sound has energy. If you've ever pulled up to a red light next to somebody who decided that his music should be shared with the world, and the entire road is shaking, right? Your car is shaking. You know what I'm talking about? We've got a red light down the hill from our house. Our house is up on a hill. Backyard kind of goes downhill, and then cars get stopped at red lights. And inevitably, about 10:30, when everybody should be getting ready to go to sleep, some individual will pull up to the red light, and the whole house is shaking up at the top of the hill. And well, that's energy, right? Sound has energy. And if we were to take the flow of energy, well, again, if that energy flows over a long period of time, no big deal. But if there's a lot of energy in a short period of time, well, energy, work per unit time, we call that power. So sound waves then do have power in them. And if we were to take the flow of energy per unit time or power per unit area, we have something called intensity. That's the next term I need you to get in your notes. Intensity. The intensity of sound is the flow of energy per unit time per unit area. The flow of energy per unit time per unit area. Again, a shock wave, in a sense, really technically should have the same flow of energy as all the other waves that a plane would emit, right? The difference is you hear the roar of the airplane. Well, that's a certain flow of energy, but the waves aren't hitting you at one time, right? There's a series of the compressions and rarefactions versus they all kind of hit at once and there's this jumbled displacement. Well, now you've cut down on the amount of time that the energy has to hit, and so you've upped the amount of intensity. Since flow of energy per unit time is called power, we could say that intensity can be found by dividing the power of the wave per unit area. Power per unit area. If the power were spread out over a larger area, the intensity would not be as great. Over a smaller area, the same amount of power produces a higher intensity. The main thing we take away from this, though, is the units for intensity. Because we know that power, class, going back to chapter 11 in our minds, was measured in watts. I love my wife, watts and watts. It's powerful watt. And area is measured in meters squared. So that intensity then is going to be measured in watts per meter squared. Intensity is measured in watts per meter squared. Now, there's a couple different things that can cause sound to have greater intensity, to have greater power. One of those things is if you give the molecules a greater displacement, greater energy, if you will, greater amplitude. Remember, displacement from equilibrium. So, right? As you whisper, the displacement's very, very slight. As you begin talking louder, you're forcing a little bit more air out. You're giving more of a jolt, if you will, to the actual atoms and molecules. The compressions and rarefactions are more pronounced. If you continue to increase, you're getting louder. You get the idea the amplitude makes a difference, right? And that's the difference between something being very loud or something being very soft. So amplitude, first of all, affects the intensity of sound. Higher amplitude, greater displacement of molecules from their equilibrium position will give a greater intensity. But there's a second factor. Imagine taking the exact same amplitude, but causing the waves to oscillate, the particles to oscillate more rapidly. Same amplitude, but a more rapid displacement would then cause more energy as well. Well, higher frequency then would cause that. How do we perceive frequency? We're not really here yet, but going a little bit ahead, frequency we hear as pitch. Low frequencies, high frequencies, or whatever that was supposed to be, right? Higher frequencies have a greater intensity as well. This is why if a tuba blasts out a loud note, nobody really cares too much. Well, I shouldn't say that. There was a kid one time, we were at, our youth group went to camp. There were like a couple hundred of us, and one of the things at camp they did were music competitions. Everything was competition based at the camp. We went to sports competitions, music competitions, and one of the guys played the tuba. And there were these two guys in the back corner of the cabin, you know, the ne'er-do-wells. And so the alarm or whatever had gone off to say it's time for everybody to wake up, let's get moving to breakfast and devotions coming up soon. And these two guys were still laying in bed, they weren't getting up. So our youth pastor borrows the tuba. He doesn't play the tuba, but he borrowed the tuba. He was full of hot air at least. And he goes right back to where these two guys are, and he just lays as much air as he can into this tuba. And I literally watched, I didn't see the guy in the bottom bunk, but the guy in the top bunk, I literally watched his body rise in its laying position, rise out of the bunk. It was the craziest thing I'd ever seen. So, I mean, I guess a tuba could disturb you if you're trying to sleep. But in general, right, if a good person blasts a loud note on a tuba, it doesn't necessarily like, that hurts. But the piccolo, the high-pitched sound, that's kind of piercing, right? We think of that as piercing. The soprano in the opera shatters the glass, right? It's not the contrabass. They might be singing at equal amplitudes or volumes, but there's something that's just slightly deafening about the soprano singing in her, I'm not even going to try to imitate it, voice, right? We get that idea that higher frequency is the second factor that affects sound intensity. So both amplitude and frequency affect intensity. Amplitude and frequency. A couple of key intensities that you need to know. One of them is called the threshold of hearing. The threshold of hearing. This would be the softest intensity, the lowest intensity that a healthy human ear can detect. And it's 1 E-12 watts per meter squared. 1 E-12 watts per meter squared. Very, very low intensity. That's a trillionth of a watt per square meter. Okay, that's my best replication of the threshold of hearing. And my next one is more, just kidding, I'm not going to do it to you. The next one is that we'll know that we need to know is called the threshold of pain. Okay, this is what makes your ears not literally bleed, but you've heard of course my wife says sometimes my singing makes her ears bleed. But anyway, that's usually when I decide to do soprano and bass in the same song and jump back and forth and go falsetto. She hates my falsetto. I don't think it sounds that bad, but she does not care for it. The threshold of pain would be a full watt per square meter. So 1e negative 12 watts per square meter that you're just barely able to hear. You get up to 1 full watt per square meter and pain is being caused. This is if you ever had the misfortune to not have ear protection on at the gun range for a moment and somebody, maybe the range was cold and somebody wasn't paying attention and they fired, which is really dangerous, but they fired a shot and you didn't have ear protection on, that can really hurt, okay? I did that to my uncle once, poor guy. He was showing me a new gun he got. I was out shooting it, and I was stupid because guys are stupid sometimes. I didn't wait for him to get his ear protection on, and he was right next to that gun. I felt so bad. I was just excited. I was like, oh boy, I can shoot his gun. This is cool, yeah. And I didn't wait, and he didn't have time. Anyway, pain, okay? Airplane flies low overhead, maybe at a Blue Angel show, or they used to do Thunder in the Valley here, I was told. I've never been to one of those, and they haven't done it in years. Anyway, but I heard about Thunder in the Valley. By the way, intensity of sound, broken windows, I heard. I think that's why they stopped doing it. But that can cause pain to your ears, especially the little ones. Can have hurting ears. You would have been pretty little back when they last did it, because I've been here 13 years, and I think they did it 1 or 2 of the years I was here. I just didn't get to be there for it. Of course, I was spoiled on Blue Angel air flights anyway, so to me. Anyway, but pain, okay, 1 watt per square meter threshold of pain. But we get this idea as well. If you were, when the jets, for instance, in Thunder in the Valley, fly high overhead, you hear the roar of the plane. By the way, have you ever noticed you see them and then you hear them later, right? So it's kind of neat that you can, you see them coming and then the roar kind of starts to hit you. That is painful, but it's more painful when they come down low overhead, correct? When it's closer, kind of like the PE whistle, speaking of frequency, right? High-pitched whistle. Okay, if it's right in your ear, it hurts worse. Well, I already alluded to this when we talked about 1, 2, and 3-dimensional waves, but why is that? Because a 3-dimensional wave-like sound will diminish. It'll weaken as it spreads outward from the source, right? Because it's spreading outward in all directions. So because sound is a 3-dimensional wave, this intensity is proportionally varied with the distance. But it's not just proportional to the distance, it's a squared relationship. So as for instance, a person who's twice as far away will hear a 4th as intense a sound. 3 times as far away would hear a 9th as intense a sound. The relationship is that intensity is proportional inversely to the square of the distance from the source. That leads us then to the next equation. I guess technically this is an equation we'll use a little bit, but to a major equation we'll use in this section, and that is I1R1 squared equals I2R2 squared. The intensity at a certain distance squared equals the intensity at another distance squared from that source. Again, don't forget the squared relationship on the radius. A 2-dimensional wave will weaken in accordance with its radius, inversely. 3-dimensional, the radius is squared, and that's what we're dealing with sound waves. Take a look at page 265, if you would. Let's look at problems using both of these equations. Problem number 9, first of all. Read it for us, Audrey.
What is the sound intensity of a 1e negative 2 watt sound wave flowing through a surface 10 meters by 5 meters?
All right, so here they're looking for intensity. They give us the power, and they also give us the dimensions. Maybe this is a massive window that's 10 meters by 5 meters, and or whatever the surface happens to be. But if they give us the dimensions, then we can find the area, right? If it's 10 by 5 plus, what's the area of this particular surface? 50 square meters, right? So they give us the power. It was what again? 1e negative 2?
Yes.
1e negative 2 watts. And it was flowing through a surface that was 50 square meters. Well, at your seats, what's the intensity of that particular sound? And what do we get?
0.0002.
Good. Or we could say 2e negative 4 watts per square meter. Okay? pretty easy. We're not going to do a lot with this equation, but pretty straightforward math, right? And of course, if we wanted power, we could multiply cross-sectional area by intensity or alternate if we wanted to the cross-sectional area, but not an equation we'll use a whole lot. More so what we see in number 10. Read that one for us, Kendall.
A sound has an intensity of 4 e negative 10 watts per meter squared at 2 meters. What is its intensity at 3.10 meters?
All right, so I mean, 4e negative 10, we can remember 1e negative 12 is the threshold of hearing. All right, so at 2 meters away from Michael, this is maybe somewhere around what 4e negative 10 would be. What if I take a step backwards, stay with me, I'm at 3 meters away. Okay, so just a little bit further away, the intensity will drop. Let's see what that intensity would be very quickly. So we take the intensity, the first intensity given class,
The 4e negative 10.
and that was at a distance of 2 meters, but we have to square it. 4, and we're going to find the intensity at, what was the distance? 3.1 meters, but we have to square that on the calculator. 9.61. All right, so we'll multiply, we'll divide out the 9.61. And what intensity would you hear, or would there be, excuse me, would be a better way to put it, because what we're going to talk about tomorrow, I think I did something on 4e negative 10 times 4. Right, 9.61. There we go. And it already put it back in scientific notation for me, which was nice, class.
1.66 e negative 10.
Good, 1.66 e negative 10 watts per square meter. We can see it more than cut the intensity in half, right? Half the intensity would be 2 e negative 10. It more than cut it in half just by stepping back another meter or so. All right, homework for this evening is to read pages 259 to 264. Read pages 259 to 264. And on page 265, answer questions 18, 19, and 22. Page 265, questions 18, 19, and 22. All right, have a wonderful rest of your day. You are dismissed.